Empty space is pushing on the walls of the universe right now. We are about to explore the quantum vacuum, the hidden engine of reality where nothing is everything. By the end, you will understand how the complete emptiness around you creates forces that shape atoms and may power the cosmos. We will see how two metal plates in a void can snap together by themselves, and why the blankness of space might hold the secret to its own explosive growth. What does true nothingness look like to you now? For centuries, the greatest minds believed a perfect void was possible. Aristotle argued that nature abhorred a vacuum, a concept that held sway for nearly 2,000 years. Isaac Newton later envisioned space as a fixed, absolute stage, an empty container where celestial bodies performed their motions. This was the classical vacuum, a true and absolute nothingness. It was a comforting idea, a backdrop of pure stillness, but the quantum revolution tore that backdrop down. What we call a vacuum today is not the absence of everything, it is the ground state of everything. It is the lowest possible energy condition, but in the quantum world, lowest does not mean zero. Think of it like a calm sea on a windless day. From a distance, the surface is glassy and still, a perfect sheet of nothing. But dive beneath, and you find a realm of constant motion, with currents shifting and molecules forever vibrating. That sea is not empty, it is simply at its most quiet, most fundamental level of activity. The quantum vacuum is that sea. It is not empty space, it is space filled to the brim with fundamental fields. These fields, for the electron, for light, for every particle we know, are not things that come and go. They are permanent fixtures of reality, woven into the fabric of the cosmos itself. Even when no particles are present, these fields are there, and they are never truly still. They undergo fleeting, spontaneous fluctuations, a kind of quantum jitter. This means the blank stage Newton imagined is in fact a seething, energetic foundation. This is the first and most crucial shift in understanding. True emptiness is an illusion. What looks like nothing is actually the most something it can be without tipping over into the world of stable particles we see. This foundational idea changes everything, because if the void is not empty, then what forces might it hide? This constant hum is the soundtrack of reality itself. To understand it, we need to peek at the quantum toolkit. Forget the idea of tiny billiard ball particles floating in empty space. In our modern view, the fundamental ingredients of the universe are not particles but fields. Imagine the entire cosmos as a vast, invisible ocean. This ocean is not made of water, but of countless different fields layered atop one another. There is an electron field, a photon field, a quark field, one for every type of particle we know. These fields are everywhere, stretching through every point in space. What we call a particle, like an electron or a photon of light, is not a separate object, but a localized ripple or wave in its corresponding field. A calm electron field means no electrons are present, but excite that field, give it a specific packet of energy, and a ripple appears. That ripple is what we detect as an electron. So particles are not things in the field, they are the field itself, momentarily stirred into a specific pattern. Now, here is the profound part. Even when a field is perfectly calm, when there are no ripples we would call particles, it is never completely silent. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, tells us there is a fundamental limit to how much we can know. We cannot precisely know both the position and the momentum of a quantum system. More broadly, we cannot know both its energy and how long it possesses that energy with perfect certainty. This has a stunning consequence for our fields. It forbids them from ever having exactly zero energy. If a field were perfectly still, with zero energy and zero fluctuation, we would know both its state and its change in state with absolute precision, which the universe simply does not allow. So every field, even in its quietest possible state, its ground state, must possess a minimum, irreducible jitter. This is zero-point energy, a permanent background vibration woven into the fabric of space. This is not just a mathematical quirk. This zero-point energy has real, physical teeth. It means the quantum vacuum is not a static void, but a dynamic medium buzzing with fleeting activity. For impossibly brief moments, these fluctuations can borrow energy from nowhere, creating temporary particle-antiparticle pairs that wink into and out of existence before the universe can reclaim the debt. This sea of virtual particles is the raw material. It is the first concrete clue that nothingness is not passive. It is an active, energetic foundation, a stage that is never truly dark, always humming with potential. And if this sea can spontaneously create temporary visitors, what happens when we place something real into it, something that can interact with this hidden energy? The answer leads us to one of the strangest forces in physics, born not from matter, but from the restless nature of nothing itself. The quantum vacuum hums with a kind of creative debt. To make sense of its restless activity, we must meet its most famous actors, the virtual particles. This name is wonderfully misleading because they are not particles at all, at least not in the way we normally think. They are better understood as temporary disturbances, fleeting ripples in the quantum fields we just described. The uncertainty principle that forbids perfect stillness also grants a peculiar lone program. It states that for a very, very short span of time, the amount of energy in a system can be uncertain. Think of it like the universe's own financial system, where energy is the currency. The vacuum can borrow a tiny amount of this energy from nowhere, but it must repay the loan almost instantly. The more energy it borrows, the faster it must repay. This is the energy-time uncertainty relation. It is the rule that allows something to come from nothing, if only for a heartbeat. Picture a crowded, ancient marketplace. Vendors and customers are constantly exchanging coins. For a split second, a coin might leave one hand before it lands in another, existing in a state of transfer, belonging to neither person fully. That coin is like the borrowed energy. The entire marketplace buzzes with these momentary transactions, a blur of lending and repayment that never stops. In our quantum marketplace, the borrowed energy momentarily excites a field, creating a pair of disturbances. Crucially, these disturbances often appear as matched pairs, a particle and its antiparticle, like a virtual electron and a virtual positron. They are two sides of the same quantum coin. They flicker into existence together, dance for an unimaginably brief moment, and then annihilate each other, returning the borrowed energy to the vacuum ledger. Their entire lives are measured in fractions of a second so tiny they make a nanosecond feel like an eternity. You cannot see them directly. If you tried to catch one with a detector, the act of observation itself would supply the energy to make it real, repaying the universe's loan and turning the virtual particle into a real one. So they are not hidden matter. They are the vacuum's transient activity, the shimmer on the surface of that deep, calm sea. Yet to call them merely a mathematical trick would be a profound mistake. While they cannot be put in a bottle, their indirect signature is written across reality. These fleeting entities are the active agents of the empty space. They are the medium through which forces are communicated, the ghostly messengers that carry the fundamental interactions of nature. And when we place real, solid objects into this buzzing quantum foam, these virtual messengers can create a startling effect. They can push those objects together or pull them apart, generating a real, measurable force from the apparent nothingness between them. This is not a theoretical fantasy. It is a verified phenomenon, and its discovery begins with two simple metal plates held apart in a perfect void. What happens next reveals the true power of the quantum vacuum. The stage was now set for a ghost to reveal its hand. In 1948, a Dutch physicist named Hendrik Casimir, working alongside his colleague Dirk Polder, made a startling theoretical prediction. He proposed that two flat, perfectly smooth metal plates, placed parallel to each other in a complete vacuum, with no external forces, no electric charges, and absolutely nothing between them, would spontaneously move. They would be pulled together by an invisible force emanating from the empty space itself. At the time, this seemed like a fringe idea, a curious mathematical result from the new and strange rules of quantum theory. But it was the first precise blueprint for a machine powered by nothingness. The genius of the Casimir setup is its simplicity. Imagine two gigantic, flawless mirrors facing each other in the dark void of space, separated by a gap narrower than 1,000th the width of a human hair. This gap is not just empty, it is a vacuum chamber purged of every atom of air. Yet, according to quantum theory, it is still filled with the humming electromagnetic field and its virtual photons, the fleeting particles of light that constantly wink in and out of existence. Now, here is the crucial twist. These virtual photons are not just random noise. They behave like waves, and waves have specific wavelengths. When you confine waves, you force them to adopt only certain patterns. Think of a guitar string, pluck it, and it vibrates with a fundamental note and its harmonics. It cannot produce just any random sound, only the notes where the wave fits perfectly between the two fixed ends. The space between Casimir's metal plates acts exactly like that guitar string, but for the waves of the quantum vacuum. The plates, being perfect conductors, impose a boundary condition. They force the electromagnetic field to be zero at their surfaces. This means only those virtual photons whose wavelengths fit perfectly into the gap, whose waves are a whole fraction of the distance between the plates, can exist in that narrow corridor. They are the allowed notes in this tiny quantum instrument. Outside the plates, in the vast open space, there is no such restriction. The vacuum fluctuations there can have any wavelength imaginable, from the incredibly short to the astronomically long. This creates a profound imbalance. Inside the gap, the menu of possible virtual particles is limited. Outside, it is a boundless feast. The relentless pressure of this more diverse, more energetic sea of fluctuations outside the plates is greater than the pressure from the limited set of fluctuations trapped inside. The result is a net push from the outside, forcing the plates together. It is not that the vacuum between the plates is sucking them in. It is that the unbridled activity of the vacuum everywhere else is pushing them together, because the plates themselves have edited the guest list for the quantum party in the space between them. For decades, this remained a beautiful theoretical prediction. Then, in the late 1990s, with technology finally catching up to theory, a team led by physicist Steve Lamoreaux performed a landmark experiment. With exquisite care, they measured the force between a metal plate and a metal sphere, a geometry that simplifies the math but tests the same principle. The result was unambiguous. The plates moved. The force matched Casimir's prediction with remarkable precision. The ghost had left a fingerprint. Empty space had reached out and exerted a real, measurable force. This was not philosophy, it was physics. The void was not passive. It was a dynamic medium whose energy could be shaped and harnessed simply by changing the geometry of space itself. If placing two plates close together can create such a force, what other shapes could we sculpt in the vacuum, and what other impossible energies might they reveal? The Casimir effect had been a ghost in the equations for half a century. Turning that phantom into a measurable fact required confronting an almost absurd level of subtlety. The force it predicted is incredibly weak, becoming significant only when objects are brought within a few hundred nanometers of each other, a distance less than the wavelength of visible light. At that scale, the attraction between two plates is comparable to the weight of a single bacterium. Detecting such a whisper meant eliminating every other conceivable whisper, every source of noise from vibrations, static electricity, and even the gravitational pull of a person walking past the laboratory. It was a challenge of pure precision, a search for a signal buried in an ocean of interference. This is where the work of physicist Steve Lamoreaux and his team in 1997 became a landmark. Their ingenious setup was a masterpiece of isolation. They used a torsion pendulum, a device where a horizontal bar is suspended by a thin, flexible fiber. At one end of the bar, they mounted a smooth, spherical lens made of quartz and coated with a layer of gold. They then carefully brought a flat, polished silica plate coated with the same metal close to this sphere. The key was that the Casimir force between a sphere and a plate, while similar in origin, has a simpler mathematical form to verify. As they moved the plate closer, the predicted attraction would cause the torsion fiber to twist by a minuscule amount. To measure this twist with the required fidelity, they used a laser beam reflecting off a mirror on the pendulum, turning an angular shift into a visible movement of a light spot across a detector. But even this was not enough. They had to account for the residual electrostatic forces that could easily swamp the quantum signal, a problem they solved with sophisticated electronic feedback systems. After painstakingly subtracting all known forces, a clear, persistent attraction remained, one that matched Hendrik Casimir's 50-year-old prediction with an uncertainty of only about 5%. The void had spoken, and we had finally heard it. Today, the quest to measure vacuum forces has moved into the microscopic realm. Researchers now employ tools like the atomic force microscope, a device with a tip so sharp its point can be a single atom. By scanning this tip over a surface at nanoscale distances, scientists can map the Casimir force directly, feeling the gentle push and pull of the quantum vacuum like a blind person reading Braille. Other experiments use micro-electromechanical systems, or MEMS, which are tiny mechanical devices etched onto silicon chips. These can have moving parts separated by gaps precisely engineered to be on the order of 100 nanometers. When released, their movement is dictated not just by classical springs, but by the invisible quantum pressure from empty space itself. In experiment after experiment, across different geometries and materials, the result holds. The measured force aligns with theory, a testament to the reality of the effect. This is far more than confirming a curious prediction. It is solid, empirical proof that the quantum vacuum exerts real pressure. That which we call nothing is a dynamic entity with tangible mechanical consequences. The Casimir effect transformed from a theoretical curiosity into a cornerstone of quantum electrodynamics, the most precisely tested theory in all of physics. It shows us beyond any doubt that the vacuum is not a passive stage. It is an active participant, a medium whose energy density can be shaped by boundaries and geometry, pushing on the very walls of our reality. If simply placing two plates close together can summon a force from the void, what happens when we consider the most profound boundary of all, the edge of the observable universe itself? But the story does not end with two flat plates. That was merely the simplest melody the quantum vacuum can play. The true symphony of empty space reveals itself when we change the shape of the instruments. The Casimir force is not a single, universal attraction. It is a rich and complex phenomenon dictated entirely by geometry. Think of the vacuum fluctuations as an invisible fluid, constantly lapping against all surfaces. The force you feel depends on how you sculpt the containers that hold this fluid. While two parallel plates attract, other shapes can create different, even stranger, outcomes. For experimental physicists, measuring the force between two infinite plates is practically impossible. How do you align perfection and bring infinity into a lab? The solution was an elegant shift in geometry. By using a smooth sphere and a flat plate, scientists created a configuration that is far easier to manage. The curvature of the sphere means that at the closest point the gap is microscopic, but it quickly widens. This simplifies the calculations and, crucially, amplifies the measurable effect at that single point of near contact. This sphere-plate geometry was the key that unlocked the first definitive laboratory observation, turning a theoretical ghost into a concrete measurement. Yet the real surprise is that the vacuum force is not always attractive. Under the right geometric conditions, it can become repulsive. Imagine a perfectly conducting sphere and a flat plate made of a specific material, one that interacts with the electromagnetic field in just the right way. In such a case, the menu of allowed virtual particles can be arranged so that the pressure outside the gap is actually less than the pressure inside. The result would be a net push forcing the objects apart. This is not science fiction. Theoretical work by physicists like Evgeny Lifshitz provided a more powerful framework that goes beyond Casimir's ideal metals. Lifshitz's theory accounts for the real-world properties of materials, their finite conductivity, and even the influence of temperature. It treats the materials as having specific electromagnetic responses, which act like filters, selectively amplifying or suppressing certain wavelengths of the virtual particle C. This reveals a profound truth. The quantum vacuum is not a one-size-fits-all background. It is a pliable medium. By choosing our materials and sculpting our shapes, we are not just observing a force, we are programming the vacuum's behavior. We are editing the guest list for the quantum fluctuations in a specific region of space. This transforms the Casimir effect from a curiosity into a frontier of engineering. In the realm of nanotechnology, where devices are built atom by atom, these vacuum forces are no longer a subtle whisper. They become a dominant, often problematic voice. The tiny moving parts of a future micromachine, separated by mere nanometers, could stick together permanently due to this relentless quantum attraction, a phenomenon known as stiction that is a major hurdle for nanoscale engineers. But with the understanding from Lifshitz's theory, the challenge becomes an opportunity. Could we design nanostructures with specific geometric shapes and material coatings to induce a repulsive Casimir force? Imagine components that hover on a cushion of nothingness, with quantum vacuum pressure itself preventing contact and eliminating friction. This is the emerging field of vacuum engineering, where we manipulate the properties of empty space to achieve a desired mechanical effect. We are learning that the void is not an obstacle to be overcome, but a new kind of tool to be shaped. If we can engineer repulsion from emptiness, what other impossible feats might the vacuum enable? The answer may lie in the grandest geometry of all, the shape of the cosmos itself, where the vacuum's energy is not pushing on plates, but on the very fabric of space-time. The quantum vacuum is not the only performer on this dark stage. There is another, more familiar source of energy that fills our world, one we feel on our skin every day: heat. At the heart of our warm, bustling reality lies a fundamental connection between temperature and the void, a bridge that ties the quantum realm directly to our everyday experience. This is the story of the thermal Casimir effect, where the cold ghost of quantum fluctuations meets the warm glow of thermal radiation. To understand it, we must first revisit the idea of a perfect vacuum at absolute zero, the temperature where all classical molecular motion ceases. In that state, the only activity is the quantum jitter, the zero-point fluctuations we have been exploring. The force between two plates in that frozen void is purely quantum, a whisper from the ground state of reality itself. But our world is not at absolute zero. We live immersed in a bath of thermal energy. Every object at a temperature above absolute zero, including the walls of this room, your own body, and the very air, emits a faint glow of electromagnetic radiation. We call this thermal radiation, and it consists of real photons being constantly emitted and absorbed. At room temperature, these photons are mostly in the infrared part of the spectrum, invisible to our eyes but detectable as warmth. Now place two metal plates in this warm environment, not in an ideal frozen vacuum, but in the world we actually inhabit. Suddenly, the space between them is filled with two choirs singing at once. The first choir is the eternal quantum hum of zero-point fluctuations. The second, new choir is the symphony of thermal photons, real electromagnetic waves generated by the heat of the plates and their surroundings. These thermal photons also behave as waves, and they are also subject to the boundary conditions imposed by the plates. Just like their quantum counterparts, only certain wavelengths fit perfectly into the gap. This means the thermal radiation itself can be enhanced or suppressed in the space between the plates, creating an additional pressure, a thermal contribution to the Casimir force. This thermal force is not a separate phenomenon. It is a direct and inevitable consequence of bringing temperature into the equation. Its character changes dramatically with distance. At the nanoscale separations where the pure quantum Casimir effect reigns supreme, the thermal contribution is almost negligible. The quantum whisper is still the loudest voice. But as you pull the plates farther apart into the micrometer scale, something fascinating happens. The thermal photons, with their longer wavelengths, begin to dominate the conversation. The force you measure transitions from being primarily a quantum mechanical effect to being primarily a thermodynamic one. It is a seamless handoff from the realm of Heisenberg to the realm of classical heat. This interplay reveals a profound unity. There is no sharp boundary between the quantum vacuum and the warm classical world. They are woven together, two aspects of a single, coherent reality. The force you feel between two surfaces in a lab at room temperature is a hybrid, a sum of the eternal quantum jitter and the familiar dance of thermal energy. This means the ghostly pressure of empty space is not just a curiosity for cryogenic laboratories. It is active here and now, subtly blended into the forces that operate in the microscopic machinery of our warm world. It is a quiet reminder that the quantum vacuum is not some distant, alien concept. It is the foundation upon which our thermal reality is built, a hidden layer of activity that persists even as the warm glow of everyday life fills the space above it. If the heat from our own bodies can influence the forces born from nothingness, what other invisible threads connect our tangible world to the quantum depths below? The warmth of our world and the chill of the quantum void are two sides of the same coin, but the influence of these vacuum fluctuations extends far beyond specialized laboratory plates. In fact, you are experiencing their effects right now, holding this very script together. To see this, we must shrink our perspective from plates and spheres down to the realm of atoms and molecules, where the quantum vacuum reveals its most intimate and familiar face. We call these the van der Waals forces. You might recall the name from a chemistry class, a vague label for the weak attractions that hold certain molecules together or allow a gecko to walk up a wall. But these forces are not some separate, mundane rule. They are the atomic scale cousins of the Casimir effect, born from the exact same restless heart of nothingness. At the core of van der Waals' attraction lies a beautiful quantum dance. Consider two completely neutral atoms, like two atoms of noble gas argon. They have no permanent electric charge, no obvious reason to stick together. Yet they do feel a gentle pull when brought very close. Why? Because even in a neutral atom, the cloud of electrons surrounding the nucleus is not a static, frozen shell. It is a dynamic quantum probability cloud. The Heisenberg uncertainty principle ensures the electrons are never perfectly still. Their positions are constantly fluctuating. For an infinitesimal moment, these fluctuations can create a temporary imbalance, a fleeting region of slightly negative charge on one side of the atom and slightly positive charge on the other. This is a temporary or instantaneous dipole. It is a direct consequence of the quantum jitter within the atom itself. Now, here is the magic. This temporary dipole in the first atom creates a tiny, flickering electric field that extends into the space around it. That field travels at the speed of light and reaches the second atom. When it arrives, it polarizes the electron cloud of that second atom, inducing a complementary temporary dipole in it. For that brief instant, the two dipoles are aligned in a way that creates a net attractive force between them. This specific mechanism is called the London dispersion force, named after the physicist Fritz London, who explained it in the 1930s. It is not a push and pull of permanent magnets. It is a synchronized shimmer, a correlation of fluctuations mediated by the electromagnetic field. And what is that field doing the mediating? It is the same quantum vacuum field, humming with virtual photons, that we have been discussing all along. Those fleeting virtual particles are the messengers that carry the influence of one atom's quantum jitter to its neighbor, orchestrating their momentary attraction. So where does the grand Casimir effect fit in? Think of it as the large-scale finale of this atomic-scale symphony. The Casimir force between two metal plates is not a new, different force. It is what you get when you add up the London dispersion forces between every single atom in one plate and every single atom in the other plate, across the vast microscopic landscape of their surfaces. At very short ranges, we describe the attraction atom by atom as van der Waals forces. But as the objects get larger and the separation increases, it becomes impossible and impractical to count each atomic interaction. The collective effect smooths out into a force that depends only on the overall geometry and material properties of the bodies. The Casimir effect is the macroscopic, long-range limit of the van der Waals force. This connection is a revelation of breathtaking unity. It shows us that the same fundamental principle, quantum vacuum fluctuations, is the silent architect of forces across an immense range of scale. It is the reason inert gas atoms can form liquids at low temperatures. It is the reason graphite layers in a pencil lead slide against each other. It is the reason two metal plates in a vacuum snap together. From the angstroms that bind molecules to the nanometers that pull on nanomachines, it is all the same ghostly hand, writing the rules of attraction with the energy of empty space. If these fluctuations can orchestrate the structure of matter itself, what other cosmic structures might they be quietly holding together or perhaps pushing apart? This leads us to a question that feels almost forbidden. If the vacuum is a dynamic medium, a sea of fluctuating energy, then what happens when you try to move through it? Does empty space itself create a kind of friction? The very idea seems to violate a sacred principle of physics. In the classical universe of Newton and Einstein, an object moving through a perfect vacuum at constant velocity should continue forever untouched, experiencing no drag. The vacuum offers no substance to push against, but our quantum vacuum is not empty. It is filled with fields and their fleeting virtual particles. So, could an object swimming through this quantum sea feel a gentle resistance, a subtle drag from the vacuum itself? This speculative frontier is known as quantum friction or vacuum damping. The theoretical answer is subtle and depends entirely on how you move. A perfectly smooth, featureless object gliding at a perfectly constant speed through a perfect vacuum may, according to some calculations, feel no net force. It would be like a perfectly streamlined ship slipping through a calm ocean without making a ripple, but introduce any imperfection, any acceleration, and the picture changes dramatically. Imagine that same object suddenly speeding up or changing direction. Acceleration is a kind of violence against the background fields. It can stir the quantum vacuum in a profound way, exciting real particles out of the void. One stunning prediction is that an accelerating observer would perceive the once calm vacuum as a warm bath of radiation, a phenomenon known as Unruh radiation. For the object itself, this excitation acts like a loss of energy. It must pay a tiny toll to the vacuum for its change in motion, emitting photons and slowing down as if pushing through a subtle quantum treacle. Similarly, a surface that is not atomically smooth, and no real surface ever is, has tiny bumps and valleys at the quantum scale. As it moves, these imperfections can scatter virtual photons, converting some of the object's kinetic energy into real electromagnetic waves. It would be like dragging a comb through still water. Even if the water offers no classical resistance, the act of moving the comb through it creates ripples, and making those ripples takes energy from the comb's motion. While this quantum friction has not yet been conclusively observed in a lab, its effects are incredibly faint, masked by every other force. The theoretical possibility is profound. It suggests that the very concept of inertia, an object's resistance to changes in its motion, might not be a fundamental property of mass alone. Instead, inertia could emerge from an object's interaction with the quantum vacuum field. To accelerate is to disturb this field, and the field pushes back. This idea that the ghostly hum of nothingness might be the origin of our most basic experience of mass and motion is a breathtaking connection. It hints that the quantum vacuum is not just a backdrop for physics, but may be the source of physics itself. If motion through the void can be dampened by its own hidden energy, what does that say about the motion of the largest thing we know, the universe in its first moments of existence? The ultimate test of this restless void is not just to feel its push, but to make it speak. What if you could shake the vacuum so violently that its ghostly whispers became a shout of real light? This is the promise of the dynamical Casimir effect, a prediction where motion itself tears photons from the fabric of nothingness. The static Casimir effect shows us that boundaries shape the vacuum's energy. But if those boundaries are not still, if they are moving, they do more than just shape the energy, they can amplify it. Imagine a mirror, but not one sitting passively in a lab. Picture it oscillating back and forth, not at human speeds, but at a significant fraction of the speed of light. As it moves, it does something extraordinary to the quantum sea of virtual photons lapping against its surface. Each time the mirror moves, it changes the boundary conditions for the electromagnetic field in the space in front of it. Think of it like a loudspeaker cone vibrating in air, but here the medium is the quantum vacuum itself. A mirror moving at ordinary speed simply reflects light, but a mirror moving at relativistic speeds, approaching a meaningful fraction of light speed, becomes an amplifier for the vacuum's fluctuations. The rapid, oscillating motion can impart energy to the virtual photon pairs that constantly wink in and out of existence near its surface. In essence, the mirror's motion can stimulate the vacuum, promoting these fleeting virtual particles into stable, real photons that fly away as detectable light. It is the quantum equivalent of rubbing your hands together fast enough to create a spark, but here your hands are the boundaries of space, and the spark is light born from pure motion in a void. For decades, this remained a thought experiment of staggering difficulty. How could anyone possibly oscillate a physical mirror at such impossible speeds? The breakthrough came not from moving a piece of metal, but from moving an electromagnetic boundary with a trick of quantum engineering. In 2011, a team of researchers in Finland and the United States performed a landmark experiment. They used a device called a superconducting quantum interference device, or a SQUID. This is not a mirror in the traditional sense, but a loop of superconducting wire that is exquisitely sensitive to magnetic fields. The key insight was that the effective electrical length of this device, which dictates how it interacts with microwave photons, could be changed incredibly fast, not by moving atoms, but by applying a rapidly oscillating magnetic field. This changing electrical length acted precisely like a mirror moving back and forth at nearly 1/4 the speed of light. They placed this squid in a supercooled environment, a near-perfect vacuum at a temperature within a fraction of a degree above absolute zero, to silence the thermal noise. Then they set their electromagnetic boundary into its hyper-fast oscillation. From the quantum vacuum surrounding the device, real microwave photons emerged. They were measured, counted, and their properties matched the predictions for photons generated from nothing but the agitated vacuum. The void had been made to glow. This was not just another confirmation of quantum weirdness. It was a direct demonstration that the vacuum is a physical medium, one that can be manipulated to extract real, measurable energy. It blurs, perhaps even erases, the line we draw between virtual and real. Those particles we call real may simply be the ones we have successfully encouraged out of the background sea, promoted by a boundary in motion or a collision of immense energy. If we can make light by shaking the boundaries of a tiny circuit, what other cosmic processes might be shaking the boundaries of the universe itself, filling it with light and matter from an initial state of apparent nothing? The light we can pull from a vibrating circuit is a whisper compared to the cosmic shout echoing from the void. To see the true power of nothing, we must scale up our view to the grandest stage imaginable, the entire universe. Here, the quantum vacuum transitions from a fascinating laboratory effect to the central character in the greatest mystery of modern cosmology. Astronomers in the late 1990s made a shocking discovery. By observing distant supernova, they found that the expansion of the universe is not slowing down, as everyone expected from the gravitational pull of all its matter. Instead, it is speeding up. Some unknown force is pushing galaxies apart with ever-increasing urgency. We call this force dark energy, and it constitutes about 68% of the entire energy budget of the cosmos. It is the dominant component of reality, and we have almost no idea what it is, but we have a prime suspect, one we have been getting to know intimately. The leading candidate for dark energy is the energy of empty space itself, the cosmological constant, a term Albert Einstein originally introduced and later called his greatest blunder. This is the quantum vacuum scaled up to a cosmic dimension. The idea is staggering in its simplicity. If every tiny cubic centimeter of space possesses a tiny, irreducible energy density from quantum fluctuations, then across the vast emptiness between galaxies, that energy adds up. And because this energy is a property of space itself, as the universe expands and creates more space, more of this vacuum energy comes into being. This could produce a repulsive pressure, a kind of anti-gravity that drives the accelerating expansion we observe. Quantum vacuum could literally be blowing the universe apart, but here we encounter physics' most embarrassing and profound disconnect, known as the cosmological constant problem. When theorists attempt a straightforward calculation of the vacuum's zero-point energy density using quantum field theory, they get a number, and that number is catastrophically, unimaginably wrong. It is too large by a factor of 1 followed by 120 zeros. To put that in perspective, it is like calculating the weight of a single grain of sand and getting an answer larger than the mass of the entire observable universe. This is not a small error. It is the worst theoretical prediction in the history of science, a screaming indication that our two most successful theories, quantum mechanics and general relativity, are fundamentally incompatible when it comes to understanding nothingness. One theory says the vacuum should be brimming with an energy so colossal it would have ripped the cosmos to shreds in an instant after the Big Bang. The other theory, when fitted to our telescope's data, suggests the vacuum energy is real but almost zero, a faint, gentle push only noticeable across cosmic distances. This discrepancy of 120 orders of magnitude is not just a puzzle, it is a signpost pointing to a deeper layer of reality we have yet to uncover. It tells us that something profound is missing from our picture, perhaps a symmetry that cancels out most of this energy, or a new principle we have not yet imagined. Yet, despite this colossal problem, the core idea holds a powerful allure. The fact that empty space has an energy density, however poorly we can calculate it, is now a central pillar of our standard model of cosmology. The quantum vacuum provides a natural, elegant mechanism for the acceleration we see. It is the something filling the void, a uniform background energy that does not dilute as the universe grows. This makes the humble quantum fluctuation, the ghost in the machine of the lab, the most significant potential force generator in all of existence. It is the leading candidate for the engine of cosmic destiny. The void is not just pushing on tiny plates, it may be pushing on the fabric of spacetime itself, shaping the ultimate fate of everything. If the energy of nothing can dictate the expansion of the cosmos, what other fundamental truths might be hidden within its impossible, silent mathematics? But the unsettling truth is that this stable ground we stand on might be an illusion. Our universe could be resting on a ledge, not in the deepest valley of reality. This leads to perhaps the most speculative, yet theoretically grounded cosmic catastrophe imaginable, a concept known as vacuum decay. To grasp it, we must think of the vacuum not as a single state, but as a landscape of possibilities. Picture a vast, rolling mountain range. Each valley in this range represents a possible stable state for the quantum fields that fill our universe, each with its own lowest energy level. Our universe, as we know it, exists in one such valley. The laws of physics we observe, the forces that hold atoms together, the very nature of light and matter, are all determined by the shape of this particular valley. It feels stable and permanent because it is the lowest point we have ever seen. But what if somewhere in this cosmic landscape there exists a deeper valley? A state of vacuum with even lower energy than our own. In our metaphor, our universe would be sitting in a high valley that seems stable, but a far deeper chasm lies just over a distant ridge. This is what physicists call a false vacuum. Our reality is stable for now, but it is not necessarily in the absolute, true ground state of existence. It is a local minimum, not the global one. The terrifying mechanism for change is a quantum process we have already met: tunneling. In the atomic world, particles can tunnel through energy barriers they classically shouldn't be able to cross. On the cosmic scale, the same principle could apply to the entire vacuum field itself. Through a random quantum fluctuation, a tiny bubble of that lower energy, true vacuum could spontaneously form somewhere in space. The moment this bubble appears, the rules change inside it. The fundamental constants of physics, the strength of forces, even the number of dimensions, could be completely different. More critically, the energy difference between our false vacuum and the true vacuum is immense. This difference releases a colossal amount of energy at the bubble's boundary. This wall of energy creates an immense pressure, forcing the bubble to expand in all directions at nearly the speed of light. Nothing can outrun it, and nothing can stop it. As it expands, it converts the false vacuum of our universe into the true vacuum, rewriting the laws of physics as it goes. From our perspective, if such a bubble were to form even in a distant galaxy, we would have no warning. One moment, the universe is normal. The next, an invisible wall of ultimate change traveling at light speed would arrive. In an instant, every atom, every force, every structure in existence would be transformed into something unrecognizable. The universe as we know it would cease to be, not with a bang, but with a silent reconfiguration of reality's most basic rules. Now, it is crucial to state this is a remote theoretical possibility. Our vacuum appears extraordinarily stable, and if such a decay is possible, the expected timescale for it to happen is likely longer than the current age of the universe by many, many orders of magnitude. Yet the mere possibility carries a profound philosophical weight. It tells us that the properties of the quantum vacuum, and thus the forces it generates, are not necessarily fixed for all eternity. The stage upon which reality plays out could, in principle, change in an instant. The very constants we rely upon as universal might be local, contingent features of our particular valley in the cosmic landscape. This idea transforms the vacuum from a static background into a potentially volatile foundation, reminding us that the deepest nature of reality might still hold surprises we cannot yet fathom. The most convincing evidence for the quantum vacuum is not found in cosmic expansion, but in the whisper of a single atom. Decades before the Casimir effect was measured, before we could shake photons from the void, the restless energy of empty space left its signature on the most fundamental system we know, the hydrogen atom. In the 1940s, the theoretical picture of the atom seemed beautifully complete. Paul Dirac's elegant equations for the electron predicted that in hydrogen, two specific energy states of the electron, known as the 2s and 2p states, should have exactly the same energy. They were predicted to be degenerate, a perfect match. It was a clean, satisfying result from a powerful theory, but a meticulous experimental physicist named Willis Lamb, working with his colleague Robert Rutherford, decided to look closer. Using delicate microwave techniques born from wartime radar research, they probed these atomic energy levels with exquisite precision. What they found was a tiny, stubborn discrepancy. The two energy levels were not identical after all. They were split by a minuscule amount, a difference in frequency equivalent to about 1,000 megahertz, a mere whisper in the energy of the atom. This tiny splitting, now immortalized as the Lamb shift, was a crack in the flawless facade of Dirac's theory. Something was subtly altering the electron's behavior inside the atom. The explanation, developed by theorists like Hans Bethe, Julian Schwinger, and Richard Feynman, pointed directly to the quantum vacuum. Remember, the electron is not orbiting the nucleus like a planet in empty space. It is embedded in that seething sea of electromagnetic field fluctuations. Even at the absolute zero of temperature, the virtual photons of the vacuum are constantly buffeting the electron. This interaction causes the electron to jiggle slightly in its path, a tiny, frantic trembling known as Zitterbewegung, or trembling motion. This vacuum-driven jitter means the electron is not quite where the simple theory says it should be. It effectively smears the electron's position over a tiny volume. Because of this smearing, the electron feels the electric pull of the proton nucleus in a slightly different way. It spends a fraction more time slightly farther from the nucleus, where the electric force is a tiny bit weaker. This subtle change in the electron's average environment shifts its energy level by just that minuscule amount measured by Lamb. The effect is called vacuum polarization, because the virtual particle pairs in the vacuum act like a cloud of fleeting dipoles that slightly screen the proton's charge from the electron. The Lamb shift was not an external force pushing plates together. It was the vacuum's fingerprint on the internal machinery of matter itself. It showed that the vacuum's influence is woven into the very fabric of atomic structure, affecting the fundamental building blocks of everything we see and touch. This tiny shift became one of the first great triumphs of quantum electrodynamics, the theory that successfully married quantum mechanics with special relativity. The calculated value of the Lamb shift, using the full machinery of QED that accounted for these vacuum fluctuations, matched the experimental result with breathtaking accuracy. Here was direct, incontrovertible proof that the empty space within an atom is not passive. Its quantum activity is an essential player, dictating the very energy levels that define how atoms absorb and emit light. If the vacuum were truly nothing, the hydrogen atom would sing a slightly different note, and our entire understanding of chemistry and the stability of matter would be different. The void is not just around us, it is within us, quietly tuning the instruments of reality. The Lamb shift reveals a vacuum that is not just a passive stage, but a reactive medium. To understand this reaction in its full depth, we must look at how empty space itself responds to the most fundamental property in the universe, electric charge. The phenomenon is called vacuum polarization, and it transforms the simple electron into something far more complex. Picture an electron, a single point of negative charge sitting alone in the void. According to quantum field theory, it is not truly alone. The space around it is a sea of virtual particle-antiparticle pairs, constantly flickering in and out of existence. Among the most important of these are virtual electron-positron pairs. The positron is the electron's antimatter twin, identical in mass but carrying a positive charge. Now, when this cloud of virtual pairs forms near our real, negatively charged electron, something remarkable happens. The virtual positrons, being positively charged, feel an attraction toward the central electron. The virtual electrons, sharing its negative charge, feel a repulsion. For the fleeting instant they exist, these virtual particles shift their positions. The virtual positrons tend to spend their brief lives a little closer to the central electron, while the virtual electrons are pushed a little farther away. This creates a subtle separation of charge in the vacuum itself, a polarization. The space around the electron is no longer neutral. It develops a faint, shimmering halo where the vacuum's activity is skewed. This halo acts like a shield. From a distance, an observer would not see the electron's bare, fundamental charge. Instead, they would see the combined effect of the central negative charge partially surrounded by this cloud of attracted virtual positrons. The positive cloud partially cancels out or screens the electron's true negative charge, making it appear weaker from afar. This is why we call it screening. The vacuum acts like a dielectric material, an insulator that polarizes in response to an electric field. But in this case, the insulator is nothingness itself, and the polarized particles are ghosts that exist only as transient fluctuations. This screening has a profound and testable consequence. The effective charge of a particle depends on how close you look. Imagine you are an experimental physicist trying to measure the electron's charge. If you probe it from a relatively large distance, perhaps by scattering another charged particle off it, you will be interacting with the screened charge, the electron plus its entourage of virtual positrons. The force you measure will correspond to this somewhat diminished effective charge. But if you could devise an experiment to probe much closer, to penetrate deep inside that polarized halo, you would begin to see less of the screening cloud and more of the electron's bare, intrinsic charge. The closer you get, the stronger the effective electric force appears to be. This is not a flaw in our theory. It is a central prediction of quantum electrodynamics called the running of the coupling constant. The strength of the electromagnetic interaction, the fine structure constant, is not a fixed number etched in stone. It is a number that runs, changing slightly with the energy scale or, equivalently, the distance scale of the interaction. At the low energies and large distances of everyday life, it has the familiar value of about 1/137. But in high-energy collisions, where particles are smashed together with tremendous force, effectively allowing them to approach each other very closely, the measured strength of the electromagnetic interaction increases slightly. The vacuum's screening effect is being peeled back, revealing a more naked charge. This running coupling is a signature that the vacuum is an active participant, a dynamic medium that dresses every fundamental particle. It means the forces we consider constant are, in fact, subtly shaped by the invisible quantum activity of empty space. The void does not merely host the interactions between particles, it fundamentally modifies them, proving once more that what we call nothing is the most active something in the cosmos. But if the vacuum can be polarized by a static charge, what happens when we push it even further, when we subject it to motion itself? There exists a prediction so strange it seems to rewrite the rules of reality from the ground up. It states that the very act of acceleration can turn the cold void into a warm glow. This is the Unruh effect. To understand it, we must return to our two observers, but now give them profoundly different experiences of motion. Picture one observer floating freely in deep space, completely weightless. She is an inertial observer, moving at a constant velocity. She looks out at the universe with her perfect quantum detectors, tuned to the vacuum of space. She reports what we might expect: an utter and complete emptiness, a silent, dark void at absolute zero. Nothing stirs. Now, introduce a second observer. He is not floating, but strapped into the seat of a cosmic rocket, its engines firing at a constant, relentless thrust. He is accelerating, feeling a steady force push him back into his seat. He, too, looks out with identical, perfect detectors at the exact same region of space, but he does not report emptiness. His instruments detect a faint, warm bath of real particles, a thermal glow of radiation filling what his floating companion calls a perfect void. How can two people looking at the same patch of nothing see such different things? The answer lies not in the detectors, but in the nature of the quantum vacuum itself and how we define what a particle is. In quantum field theory, a particle is not an absolute, solitary object. It is an excitation, a ripple in a field, and crucially, the definition of what counts as a ripple depends on the observer's state of motion. The quantum vacuum state, that lowest energy hum we have been exploring, is defined relative to an observer who is not accelerating. For that inertial observer, the vacuum is the quietest possible state. But for an accelerating observer, the coordinates of spacetime are stretched and warped by their motion. Their very notion of time is different. When they analyze the quantum fields using their own acceleration-defined clock, the peaceful vacuum state of the inertial observer appears to them as a seething, energetic soup. The zero-point fluctuations get reinterpreted. What was a quantum jitter to the floater is reshaped by the acceleration into a spectrum of real, detectable particles with a specific temperature. The faster the acceleration, the hotter this perceived bath of radiation becomes. Think of it like two sailors on an ocean at dawn. One is adrift in a rowboat, perfectly still on the glassy water. To him, the sea is calm, smooth, and empty. The other sailor is racing across the same water in a powerful speedboat. From his perspective, the bow of his boat is slamming into the water, churning up a frothy, turbulent wake of spray and foam. The ocean has not changed, but his violent motion through it has created a turbulent, energetic environment that simply does not exist for the still observer. For the accelerating astronaut, the quantum vacuum is that ocean, and his motion through it churns virtual particles into real ones. The temperature of this Unruh radiation is incredibly faint for any acceleration we can currently produce. To feel even a warmth of 1 degree above absolute zero would require accelerations billions of times stronger than Earth's gravity. It remains, for now, a spectacularly difficult effect to observe directly in a lab. Yet its theoretical importance is monumental. It tells us that the particle content of the universe is not an absolute truth written on the fabric of space. It is a story told by an observer, a narrative that changes depending on how that observer is moving. There is no single, God's eye view of what is real and what is virtual in the quantum foam. The Unruh effect is the smoking gun for this radical relativity of reality. It is also deeply entwined with one of the most famous predictions in all of physics, Hawking radiation from black holes. The intense gravitational field near a black hole's event horizon creates a situation analogous to relentless acceleration, leading to a thermal glow where we once thought only darkness could prevail. Both effects spring from the same profound source, the interaction between quantum fields and the geometry of spacetime. They show us that the vacuum is not a static canvas, but a dynamic participant whose very meaning is shaped by motion and gravity. If acceleration can heat the void, then what other impossible transformations might be hidden within the geometry of the cosmos? The Unruh effect reveals that motion can heat the void, but gravity can do something far more spectacular. It can make a perfect darkness glow. This brings us to one of the most profound ideas in modern physics, a discovery that forever linked the quantum vacuum to the most extreme objects in the cosmos, black holes. In 1974, Stephen Hawking made a startling theoretical leap. He realized that the intense gravitational field right at the edge of a black hole, the point of no return we call the event horizon, could perform a magic trick on the quantum vacuum. It could turn virtual particles into a fountain of real radiation. To see how, we return to our sea of virtual particle-antiparticle pairs, constantly flickering into existence everywhere. Normally, these pairs annihilate each other almost instantly, returning their borrowed energy to the vacuum. But picture this dance happening right at the precipice of a black hole's event horizon. This is not a physical surface, but a mathematical boundary where the pull of gravity becomes so strong that not even light can escape. Space and time are stretched and twisted here in ways that defy our everyday intuition. Now, imagine a virtual electron-positron pair popping into existence so close to this boundary that one member of the pair forms just on the outside, while the other forms just on the inside. The particle that appears outside the horizon still has a chance. It might receive a gravitational kick, a boost of energy from the incredibly warped spacetime that allows it to escape entirely, flying away as a real particle. Its partner, born inside the horizon, is doomed. It cannot climb out. It must fall inward, carrying negative energy with it. From the perspective of the black hole, swallowing this negative energy particle is equivalent to losing a tiny amount of mass. So from afar, what we see is this, a stream of real particles, a faint glow of radiation, emanating from the seemingly empty space around the black hole. This is Hawking radiation. It means a black hole is not truly black. It has a temperature, a very low one for stellar mass black holes, but a temperature nonetheless. This single idea wove together three great strands of physics, quantum mechanics, general relativity, and thermodynamics, into a single, breathtaking tapestry. It suggested that black holes have entropy, a measure of disorder, and that they can slowly evaporate over astronomical timescales. The mightiest gravitational traps in the universe are not eternal prisons. They are slowly leaking, their immense mass dissolving into a whisper of quantum particles, born from the restless activity of the vacuum at their very edge. This process shows that no environment, no matter how extreme, can silence the quantum hum. The vacuum's creative debt operates even where gravity bends the rules of reality to their breaking point. It suggests that the fate of these cosmic giants is written not by gravity alone, but by the persistent, subtle pressure of nothingness itself. If the quantum vacuum can slowly unravel a black hole, what other impossible transformations might it be orchestrating in the hidden corners of the cosmos? Yet this cosmic evaporation is so slow it is almost a philosophical idea. To test the profound links between quantum fields and gravity, we need a laboratory where we can control the rules. This is where one of the most ingenious ideas in modern physics comes into play, the concept of analog gravity. Instead of staring into the abyss of a black hole, physicists have learned to recreate its mathematical essence in a tank of superfluid helium or a cloud of ultra-cold atoms. The key to this magic lies in a strange state of matter that behaves in many ways just like our quantum vacuum, a superfluid. Take a container of liquid helium and cool it to near absolute zero. At a critical temperature, something miraculous happens. The helium loses all internal friction, becoming a superfluid. It can flow without viscosity, climb the walls of its container, and sustain whirlpools that last forever. This happens because a macroscopic number of helium atoms fall into the exact same quantum ground state. They become coherent, moving as a single, unified quantum wave. This ground state, the quietest possible state of the superfluid, is a direct mathematical cousin to the quantum vacuum state of a field. It is the calmest, lowest energy configuration of the system. Now, imagine creating a disturbance in this superfluid, like stirring it to create a swirling vortex. That vortex is not made of different stuff. It is a pattern of excitation within the superfluid itself. In our analogy, that vortex can act like a particle, a localized ripple in the underlying quantum field. This is the core insight in both a superfluid and the quantum vacuum. What we call a particle is not a fundamental bead of stuff, but a particular kind of vibration in a universal, underlying medium. Researchers use this analogy to build stunningly precise models of cosmic phenomena. By carefully manipulating a Bose-Einstein condensate, another ultra-cold state of matter, they can create a flow where one region moves faster than the speed of sound in that medium. Just as nothing can escape a black hole once it crosses the event horizon because the escape velocity exceeds light speed, in this fluid flow, nothing can travel upstream once it crosses the point where the flow exceeds the speed of sound. This creates an artificial event horizon, and just as Hawking predicted for black holes, experiments in these setups have detected a faint thermal glow of excitations emanating from that horizon, a direct analog of Hawking radiation. They are not creating space-time warps, they are creating a fluid flow that obeys the same mathematical equations. It is a kind of quantum universe in a bottle. Other experiments use flowing water in specially designed channels to simulate the expanding universe itself, watching how waves behave as the effective spacetime stretches. These analog gravity models are more than just clever demonstrations. They provide a tangible, controllable sandbox where theorists can test the intricate mathematics of quantum field theory in curved space, a realm otherwise dominated by untestable speculation about the early universe or black hole interiors. They offer a unique window, allowing us to see how the vacuum, or something very much like it, responds to boundaries, horizons, and expansion. In these chilled laboratories, the ghostly principles of the cosmos become something we can touch, measure, and finally begin to understand. The principles of analog gravity are not just academic, they are already shaping the invisible machines of tomorrow. As we engineer devices on the scale of atoms, the gentle push of the quantum vacuum becomes an overwhelming shove. In the realm of nanotechnology, where gears and levers are measured in billionths of a meter, the Casimir force ceases to be a subtle whisper. It becomes the loudest voice in the room, a dominant force that can dictate whether a microscopic machine operates or seizes up forever. This problem has a name, Stiction, a combination of static and friction. It is the nightmare scenario for a nanoengineer. Picture a fantastically intricate microscopic motor, its components painstakingly assembled with atomic precision. The design is flawless, the materials are perfect, yet when power is applied, nothing moves. The tiny metallic gears, separated by a gap a few hundred atoms wide, are permanently locked together, not by glue or magnetism, but by the relentless pressure of empty space itself. The same quantum attraction that pulls Casimir's plates together is acting here, welding moving parts into a single, useless block. This is not a hypothetical concern. In micro-electromechanical systems, or MEMS, which are the tiny sensors in your smartphone that detect motion or orientation, stiction is a major cause of failure. A microscopic cantilever designed to vibrate and measure acceleration can suddenly snap down onto its base, silenced by the vacuum's invisible hand. A nanoscale optical switch, meant to route light in future computing systems, can find its delicate mirror permanently stuck in the on or off position. The force from nothing has become the ultimate spoiler, a fundamental law of physics that stands between a brilliant design and a working device. This forces a profound shift in engineering philosophy. Designers can no longer treat the space between components as simply empty. They must treat it as an active participant, a quantum fluid with measurable pressure. Their blueprints must now account for the shape of the void, using the lessons of Casimir and Lifshitz. They might curve surfaces to minimize contact area, or coat materials with specific films that subtly alter the vacuum's interaction, trying to engineer a repulsive effect. The ghost in the machine is no longer a metaphor. It is a critical variable in the equation for progress. This is the ultimate validation of a fundamental discovery when it moves from the laboratory journal to the engineer's manual. The quantum vacuum is no longer just a cosmic curiosity. It is a practical obstacle and a new frontier for material science, demanding that we learn to build not just with matter, but with the hidden geometry of nothingness itself. The challenge of Stiction is forcing a revolution not just in design but in ambition. Instead of merely fighting the vacuum's pull, what if we could harness its push? The ultimate goal is to move beyond mitigation and into mastery, to build machines powered not by chemical fuel or electricity, but by the subtle pressure of empty space. This is the frontier of vacuum engineering, and it begins with a thought experiment of profound elegance, the Casimir engine. Imagine a microscopic piston inside a chamber, its plates separated by a nanoscale gap. In principle, you could design a thermodynamic cycle. Start with the plates close together where the attractive Casimir force is strong. Use an external nudge, perhaps a tiny electrical pulse, to pull them apart slightly, working against the vacuum's pull. Then allow the natural attraction to snap them back together, releasing energy. If you could repeat this cycle continuously, you would have an engine that converts thermal energy from the environment into mechanical work, a motor driven by the quantum fluctuations of the void. While such a perfect, practical engine remains a theoretical dream due to immense engineering hurdles, the principle illuminates a path. It shows that the vacuum is not just an obstacle, it is a potential power source, a reservoir of zero-point energy that could, in theory, be tapped. A more immediate and transformative goal is achieving stable Casimir repulsion. Attraction locks parts together, but repulsion could make them float. The dream is to create nanoscale components that hover on a cushion of nothingness, eliminating friction and wear entirely. This is not science fiction. It is a hard materials science problem rooted in the Lifshitz theory we discussed earlier. Recall that the sign of the Casimir force depends on the materials involved. For most everyday materials, the force is attractive, but by carefully pairing specific substances with exotic electromagnetic properties, theorists have shown repulsion is possible. One promising avenue involves using materials with different magnetic responses. For instance, pairing an ordinary metallic plate with a plate made of a perfect magnetic material could induce a repulsive force. Another approach exploits the optical properties of materials at specific frequencies, essentially creating a metamaterial that makes the vacuum between two objects push harder than the vacuum outside. The geometry is also crucial. Shaping surfaces with intricate nanoscale patterns, like arrays of tiny pillars or grooves, can act as a filter for virtual photons, tuning the vacuum pressure like a musical instrument. Researchers are already experimenting with these concepts, coating surfaces with thin films and etching microscopic patterns, searching for the combination that flips the force from pull to push. The implications of success are staggering. Stable Casimir repulsion could lead to truly frictionless nanobearings, allowing the moving parts of micromachines to operate with near-perfect efficiency. It could enable levitation for micro-robotic components, letting them assemble structures without ever touching a surface. Beyond mechanics, controlled vacuum forces could become the heart of ultra-sensitive sensors. A tiny, repulsively levitated platform would be exquisitely isolated from environmental vibrations, making it ideal for detecting the faintest gravitational waves or the magnetic field of a single neuron firing. Looking further, some speculative concepts even explore vacuum forces for novel propulsion. While the forces are minuscule at human scales, for a micro-robot swimming in a fluid or navigating the bloodstream, a controlled push from the quantum vacuum could provide a gentle, fuel-free thrust. We are learning to see the void not as empty space but as a new kind of construction material. The goal is to write the recipe for vacuum, to dictate its behavior through the artistry of shape and substance. We are no longer passive observers of this ghostly force. We are becoming its architects, learning to build with the silent, persistent pressure of nothing itself. The quantum vacuum is more than a curiosity, it is a window. This restless sea of fluctuations has become our most sensitive instrument for searching the unknown, a frontier where the tiniest deviation in a predicted force could shatter our understanding of the universe. We now use the vacuum itself as a detector, hunting for whispers of physics beyond the standard model, the framework that has explained particles and forces with astonishing success for decades. The strategy is one of exquisite precision. We know with incredible accuracy what the quantum vacuum should do under specific conditions, like the exact strength of the Casimir force between two surfaces of a given material and shape. Any measured force that differs from this prediction, however minutely, is not just experimental error. It is a potential signal, a footprint left in the void by something new passing through. This search often focuses on hypothetical particles that are incredibly light and interact so weakly they have evaded every other form of detection. Consider the action, a leading candidate for dark matter. If actions exist, they would subtly alter how the quantum vacuum responds to electromagnetic fields. They could change the way light travels through a vacuum in the presence of a strong magnetic field, a phenomenon called vacuum magnetic birefringence. In this effect, empty space inside a powerful magnet would behave not like a uniform void, but like a crystal, bending light in different directions depending on its polarization. This is not magic, it is a testable prediction. If we shine a laser through a vacuum chamber surrounded by immense magnets and detect a specific, tiny change in the light's properties, it could be the action's calling card, its presence tweaking the behavior of the vacuum itself. Other experiments, like those at CERN NA64 facility, take a more direct approach. They fire high-energy electron beams into a target, searching for moments when energy seems to vanish. In the standard model, this energy should reappear as known particles, but if it disappears without that trace, it might have been carried away by an invisible particle, like a dark photon, that interacted fleetingly with the quantum vacuum fields before escaping our detectors. These are not searches for objects in space, they are searches for alterations to space. We are probing the texture of nothingness, asking if its quantum jitter follows the exact rhythm we have written, or if a faint, new beat is hidden within the hum. Even the architecture of reality is under scrutiny. Some theories propose that our universe has more than the three spatial dimensions we experience, with extra dimensions curled up at scales far smaller than an atom. These hidden dimensions would not be places you could travel to, but they would influence how fields propagate and fluctuate. Their existence would modify the spectrum of virtual particles in the vacuum, changing the precise value of forces like the Casimir effect at very short distances. By measuring these forces with ever greater accuracy at the nanoscale, we are, in effect, feeling for the shape of these unseen dimensions with the delicate touch of quantum pressure. Every experiment that pushes the measurement of vacuum phenomena to new extremes is conducting two investigations at once. It is confirming the breathtaking accuracy of our current theories, and it is listening with the silence of a void for the first crackle of something beyond. The empty space between atoms has become a cosmic auditorium, and we are tuning our instruments to hear if any new players are waiting in the wings. The most startling implication of all this is not a new force, but a new definition. For millennia, philosophers and scientists have grappled with a simple, profound question: what is nothing? The quantum vacuum has delivered an answer that shatters the classical view. It tells us that true nothingness, an absolute void devoid of any properties or potential, may not exist at all in our universe. What we have been calling empty space is not an absence, but a plenum, a state brimming with activity, structure, and latent possibility. This is not merely a technical detail, it is a philosophical earthquake. It forces us to reconsider the very foundations of reality. In the classical world, nothing was the canvas, the passive stage upon which the drama of matter played out. The quantum vacuum inverts this relationship. It suggests that the stage itself is the primary actor, and what we call matter, the particles and forces we see, are merely the most noticeable excitations, the ripples on its deep, energetic surface. From this perspective, existence itself emerges as a kind of perturbation, a localized vibration within a far more fundamental and active ground state. The electron is not a thing moving through emptiness. It is a knot of energy in a field that is everywhere. The atom is not a tiny solar system in a void. It is a stable pattern woven from the constant hum of the quantum fields. This blurs the line between something and nothing in a way that is both beautiful and deeply perplexing. Is the quantum vacuum itself a physical entity? Or is it merely a background structure, the immutable rules of the game? Philosophers of science debate this very point. Some argue it is a real, physical medium because it has measurable effects, like the Casimir force and the Lamb shift. It pushes on plates and shifts energy levels, actions we attribute to real things. Others contend it is better understood as the set of all possible states for quantum fields, a framework rather than a substance. Yet, this distinction may itself be a relic of our classical thinking. The vacuum's behavior suggests it is both, a framework that is also dynamic, a set of rules that actively participates in the game. This challenges our deepest metaphysical instincts. We are accustomed to a world of objects and the space between them. The quantum vacuum reveals a world where the space itself is the primary object, and what we perceive as separate objects are just temporary densifications of that space's inherent energy. It hints that at the most fundamental level, reality might be a unified, fluctuating whole, and our experience of separate, solid things is a kind of compelling illusion generated by how these fluctuations interact and become stable. This means the question of why there is something rather than nothing may need a subtle rewrite. Perhaps there has never been nothing. Perhaps what we call something is simply the most interesting and complex form that this eternal, quantum ground state can take. The void is not empty, it is pregnant with everything. This restless energy of the void has long escaped the lab, igniting the human imagination. Science fiction writers, sensing the profound power hidden in empty space, have woven the quantum vacuum into some of their most spectacular visions. The most famous may be the warp drive from Star Trek, a technology that does not propel a ship through space, but manipulates spacetime itself. While the show rarely delves into quantum specifics, the core idea of compressing the fabric of reality ahead of the vessel and expanding it behind resonates with a deeper truth, that space is not an empty stage, but a dynamic field that can, in theory, be shaped. This fictional concept has inspired real physicists to perform rigorous thought experiments, exploring the energy requirements and theoretical feasibility of such a geometry within the equations of general relativity, often finding a need for exotic forms of energy or matter with negative mass, properties that intriguingly echo some descriptions of the quantum vacuum's pressure. Beyond faster-than-light travel, the vacuum's promise of limitless energy is a recurring science fiction trope, Countless stories feature civilizations, often ancient and advanced, that have learned to tap the zero-point energy field, powering their cities and starships with the hum of the cosmos itself. These narratives speak directly to a deep human desire to reach beyond fossil fuels and solar panels and connect directly to the fundamental engine of reality. They cast the vacuum not as a passive backdrop, but as the ultimate battery waiting to be unlocked. This creative extrapolation serves a vital purpose. It popularizes complex scientific concepts, planting seeds of wonder in the public mind. A viewer who hears about zero-point energy in a show might later encounter it in a documentary, sparking a genuine curiosity about quantum physics. Science fiction acts as a gateway, translating the cold mathematics of field theory into the warm language of human aspiration and adventure. Yet, there exists a critical line between creative inspiration and scientific misunderstanding. The same allure that makes vacuum energy a compelling plot device also makes it a magnet for pseudoscientific claims. You may encounter bold assertions online about free energy devices that harness zero-point fluctuations, promising to power your home from the emptiness in your walls. It is crucial to understand why these claims falter. The Casimir effect does show we can extract work from the vacuum's geometry, as in the thought experiment of the Casimir engine. But that work is not free. It comes from the thermal energy of the environment used to separate the plates. The vacuum is a system in its ground state. You cannot simply dip a cup into it and draw out unlimited power without providing an equal or greater input of energy to create the necessary imbalance. The laws of thermodynamics remain firmly in place. Celebrating imagination does not mean abandoning rigor. The true value of science fiction's relationship with the quantum vacuum is not in providing blueprints, but in asking the fearless question, what if? It challenges scientists to consider the boundaries of the possible, to explore the consequences of a theory when pushed to its extreme. By dreaming of warp drives and vacuum energy reactors, storytellers keep alive the sense of awe that first drove us to ask why the plates moved and what other forces might sleep in the dark. That sense of wonder, balanced with a respect for the meticulous work of experiment, is how we navigate from the fantasies of today toward the discoveries of tomorrow. This boundless energy hums everywhere, a cosmic resource that feels almost within our grasp. Yet here lies the great quantum paradox, a sea of infinite potential that forever seems to slip through our fingers. The idea of drawing limitless power from the vacuum itself is a seductive dream, one that has fueled both brilliant science fiction and persistent misunderstandings. To see why it remains a dream, we must confront a law as unyielding as the vacuum is restless, the second law of thermodynamics. This law tells us that to extract usable work from any energy source, you cannot just have energy, you must have a difference in energy, a slope, a gradient. Think of it like a river. The water in a placid lake holds immense gravitational energy, but you cannot turn a water wheel with it. The water is all at the same level. To generate power, you need the water to flow downhill from a high point to a low point. That difference in height, that gradient, is what allows the wheel to turn. The quantum vacuum, in its pure, undisturbed state, is that perfectly flat, still lake. Its zero-point energy density is uniform and isotropic, the same in every direction and at every point in space. There is no high point and low point within the vacuum itself from which to draw a current. It is an even, unwavering hum. This is the fundamental barrier. You cannot simply plug a cable into empty space and expect power to flow, because there is no inherent flow, no downhill slope in the energy of nothingness itself. Now, this is where the Casimir effect cleverly creates a temporary, local exception, and why it is so often misunderstood. The Casimir force does not harvest energy from the uniform vacuum background. Instead, it exploits a gradient we artificially create. By placing two plates very close together, we change the rules in the narrow gap between them. We restrict which wavelengths of virtual particles can exist there. This creates a difference, an imbalance between the vacuum pressure inside the gap and the vacuum pressure outside in the open space. That difference is our energy gradient, our microscopic downhill slope. The plates move together because of that slope, and in that motion there is the potential to do work. But here is the catch: that work is not free. To reset the system, to pull the plates apart again against that strong attraction, you must put energy back in, at least as much as you got out. It is like winding up a spring. You store energy by compressing it, and you release that energy when it snaps back. The vacuum is the spring, but you still need to supply the muscle to wind it. Any practical device based on this principle, a Casimir engine, would be a heat engine, likely powered by the ambient thermal energy of its surroundings, not by magically creating energy from nothing. The dream of a zero-point energy reactor faces even deeper theoretical walls. Some proposals suggest that if you could somehow modulate the vacuum at incredibly high frequencies, you might coax real photons from it. But the devices to do such modulation, to shake the vacuum that fast, would themselves require staggering amounts of input power. The energy bill to run the shaker would far exceed the trickle of photons you might collect. It becomes an exercise in cosmic inefficiency. Furthermore, the vacuum is not just an energy source, it is part of the fundamental structure of space-time. Tampering with it on a scale large enough to power a civilization could have unpredictable and potentially catastrophic consequences, destabilizing the very quantum fields that give particles their mass and forces their strength. So while the zero-point energy of the vacuum is real and astronomically large in its totality, it is locked away by the very symmetry and uniformity that define it. It is the ultimate treasure chest with no keyhole, a reservoir we can see and even feel the pressure of, but cannot tap in any conventional sense. This does not diminish its importance, it refines it. The vacuum's energy is not for fueling our cars, it is for something far more profound. It is the foundational tension upon which the universe is built, the reason atoms are stable and forces have strength. Its value is not in what it can power for us, but in what it reveals to us about the deepest architecture of reality. The properties we take for granted, like mass itself, may be a gift from the void. This brings us to the final and perhaps most elegant connection, the link between the quantum vacuum and the origin of mass for every particle in the universe. The mechanism is known as the Higgs field, and it completes our picture of empty space not as a blank stage, but as a structured medium that defines the very nature of matter. You can think of the Higgs field as another quantum field, like the electromagnetic field, but with one extraordinary property. Unlike most fields that have an average value of 0 in their lowest energy state, the Higgs field has a non-zero average value everywhere, even in what we call a perfect vacuum. It is always on, permeating all of space with a constant, uniform presence. This persistent background value is called the Higgs vacuum expectation value. It is not a fluctuation, it is a permanent feature of the emptiness, a kind of invisible texture woven into the fabric of reality. So when we say space is empty, we must now add, except for this universal, non-zero Higgs field. This field is the reason some particles have mass while others, like the photon, do not. The interaction is beautifully analogized by a simple scene. Imagine a grand celebrity moving through a crowded, bustling room. As the celebrity walks, people turn, gather, try to shake hands or take photos. This attention creates a kind of drag, a resistance to the celebrity's motion through the crowd. The celebrity moves, but not as freely as they would in an empty hall. Now, imagine an unknown person walking through that same crowded room. No one pays them any mind. They slip through the crowd effortlessly, encountering no resistance. In this analogy, the crowded room is the Higgs vacuum, that constant background value of the field filling all space. The celebrity is a massive particle like an electron or a quark. Its interaction with the Higgs field, its way of drawing attention from it, is what we experience as inertial mass, the resistance to acceleration. The more strongly a particle interacts with the Higgs field, the more mass it has. The unknown person slipping through unnoticed is the photon, a particle of light. It does not interact with the Higgs field at all, which is why it is massless and always travels at the ultimate speed limit. This is not just a poetic comparison. It is the heart of the standard model of particle physics, confirmed by the discovery of the Higgs boson at the Large Hadron Collider. That boson is the ripple in the Higgs field, the excited state that proves the field itself is real. So mass, that most fundamental property of matter, the quality that gives objects weight and makes them resist being pushed, is not an intrinsic property of particles. It is an emergent property that arises from their interaction with a special feature of the vacuum. An electron has no mass on its own. It acquires mass by swimming through the constant, universal sea of the Higgs field. This realization ties everything together. The quantum vacuum is not just a sea of fleeting virtual particles. It is also a structured medium with permanent features that dictate the rules of the game. The Higgs vacuum expectation value is a cosmic setting, a dial turned to a specific value everywhere in the universe, and that setting determines the masses of the fundamental building blocks. It means that if you could magically turn off the Higgs field, electrons and quarks would become massless, atoms would fly apart, and the solidity of the world you know would simply dissolve. The vacuum is not just the backdrop for matter, it is the sculptor that gives matter its form. From the fleeting whispers of virtual particles to the constant hum of the Higgs field, what we call nothing is in fact the active foundation from which all something emerges. The silent hum of the vacuum is now a laboratory signal we can tune with astonishing precision. Across the globe, teams of researchers are not just observing this ghostly force, they are interrogating it, pushing the limits of measurement to ask the void new and more challenging questions. One of the most ambitious efforts is the Casimir and non-Newtonian force experiment, or CANEX, a project developed by European scientists. Its goal is profound, to measure the Casimir force not at the tiny nanoscale, but at distances up to several micrometers. Why push to these larger gaps? Because at such scales, the influence of hypothetical new forces, perhaps linked to dark energy or extra dimensions, could become discernible against the known quantum background. CANEX uses a sophisticated setup of two parallel plates, one flat and one spherical, kept in a near-perfect vacuum and cooled to cryogenic temperatures to eliminate thermal noise. By measuring their attraction with a sensitivity that can detect forces 1 billion times smaller than the weight of a single ant, the experiment aims to create the most precise map yet of the vacuum's pressure. Any deviation from the predicted curve of quantum electrodynamics would be a seismic event, a crack in our foundational model hinting at physics beyond the standard model. This is not merely checking a box, it is listening for a new instrument in the cosmic orchestra, one playing its notes in the quietest register of reality. Alongside these macroscopic probes, other frontiers are opening at the quantum scale itself. Scientists are now using clouds of atoms chilled to within a whisper of absolute zero, creating Bose-Einstein condensates where thousands of atoms behave as a single quantum wave. In this ultra-cold, coherent state, the atoms become exquisitely sensitive probes for the vacuum's influence. By studying how these atom waves scatter and interfere, researchers can infer the subtle effects of vacuum fluctuations on their behavior, testing the limits of quantum field theory in regimes where gravity might begin to whisper its own corrections. Another revolutionary approach lies in optomechanics, where tiny mechanical oscillators, some no larger than a grain of pollen, are coupled to powerful laser beams. The radiation pressure from light itself can be used to cool these oscillators to their quantum ground state, silencing the thermal jitter until the only motion left is the gentle nudging from the quantum vacuum. In these systems, the boundary between a moving object and the fluctuating field blurs, offering a direct window into how macroscopic objects interact with the void. The technological arms race driving these experiments is itself a marvel. It demands advancements in nanotechnology to craft surfaces atomically smooth, in cryogenics to create islands of profound cold, and in laser physics to generate beams of unwavering stability and power. We are learning to build instruments that are quiet enough to hear the universe's background hum. Each incremental improvement in sensitivity does two things. It confirms with ever more staggering accuracy the predictions of quantum electrodynamics, a theory whose precision is now unparalleled. But more importantly, it also opens a wider door for the unexpected. By stress testing our theories at the intersection of quantum physics and gravity, in the subtle realm of forces and fluctuations, we are probing the seams of our understanding. The quantum vacuum has become more than a subject of study. It is a benchmark, a testing ground for the very laws of nature. Every time we measure its push with greater care, we are asking the cosmos a deeper question and waiting to see if the silence holds or if it finally speaks something new. This hum of the vacuum is where our two greatest theories of reality begin to argue. Quantum mechanics paints the void as a seething sea of immense energy density. General relativity, Einstein's masterpiece, tells us that energy and mass curve the fabric of spacetime, creating what we perceive as gravity. When we try to plug the vacuum's colossal zero-point energy into Einstein's equations, we get a result so catastrophic it breaks the cosmos. The calculated vacuum energy should curve spacetime so violently that the universe would either collapse upon itself or tear apart in an instant. Our existence is a quiet, stubborn fact that proves this calculation is impossibly wrong. This is the central crisis of modern physics, the glaring incompatibility between the quantum world and the world of gravity. To resolve it, we must ask what spacetime truly is at its most fundamental level, a question that leads us to the very edge of theoretical thought. At scales far smaller than an atom at the Planck length, our smooth, continuous picture of spacetime may dissolve into something else entirely. Some approaches, like string theory, propose that the fundamental entities are not point-like particles but tiny, vibrating strings. The different vibrations of these strings correspond to different particles, and their interactions happen in a spacetime that may have extra, hidden dimensions curled up at these minute scales. In this view, the properties of the vacuum, including its energy, could be determined by the geometry of these extra dimensions, offering a potential mechanism to cancel out the overwhelming zero-point energy we naively calculate. Another path, loop quantum gravity, suggests spacetime itself is not smooth and continuous, but woven from a network of discrete quantized loops, a kind of atomic fabric of reality. At the Planck scale, this fabric would have a turbulent, foamy structure, with tiny wormholes and fluctuations constantly forming and vanishing. In this quantum foam, the very concepts of before and after or here and there could lose their meaning. The vacuum in such a picture is not a field sitting in a pre-existing container of space. Instead, both space and the quantum fields emerge together from this more fundamental, granular network. The vacuum's energy might then be a kind of thermal energy of this underlying structure, a count of its microscopic degrees of freedom. These are not just mathematical exercises. They are attempts to answer how the vacuum can be so full of quantum activity yet curve spacetime so gently. The goal is a theory of quantum gravity, a framework where the quantum vacuum and the dynamical spacetime of general relativity are two sides of the same coin. In such a theory, the smooth, classical spacetime we experience would be a large-scale average. an emergent property arising from the collective behavior of countless quantum entities, much like the smooth surface of a lake emerges from the chaotic motion of trillions of water molecules. The vacuum would be the ground state of this quantum spacetime system. Understanding it is not just about explaining a force between plates, it is about explaining how anything, including space and time themselves, can exist at all. This pursuit forces us to consider that the universe may not be built on a stage of space and time, but that space and time are built from something deeper, something quantum, and the silent hum we detect is the closest echo of that foundational layer. Even the most fundamental state of existence may be conducting a silent, cosmic computation. The quantum vacuum is not merely a seething sea of energy. It is also a specific and exquisitely organized quantum state, one rich with a hidden currency of reality, information. This perspective comes from quantum information theory, a field that asks not just what things are made of, but how they are connected. It reveals that the vacuum is entangled. To understand this, picture two regions of empty space separated by a vast distance. In our everyday view, they are independent, two separate patches of nothing. But in the quantum description, their vacuum states are not independent. The fluctuations in one region are subtly correlated with the fluctuations in the other, linked by invisible quantum threads. This is vacuum entanglement. It means that if you could perform a hypothetical, perfect measurement on the quantum fields in one region, you would instantly gain information about the fields in the other, no matter how far apart they are. This is not a signal traveling faster than light. It is a deeper, more fundamental linking that was woven into the fabric of the void from the beginning. This entanglement has a measurable quantity called entanglement entropy. It is a measure of the information hidden in these correlations, the quantum secrets shared between separated parts of the vacuum. And here, a breathtaking connection emerges. The entanglement entropy of the vacuum around a black hole's event horizon is directly proportional to the black hole's own entropy, the measure of its hidden information content first discovered by Stephen Hawking. This suggests that the mind-bending properties of black holes, their thermodynamics and their information puzzles, are not anomalies. They are extreme manifestations of the entanglement that is already present in the ordinary empty space around us. The void is not just humming, it is remembering, correlating, and processing information on a cosmic scale. This insight has led some physicists to a radical speculation. Perhaps spacetime itself is not the foundational layer of reality. Perhaps what we perceive as the smooth, continuous fabric of space and time is actually an emergent illusion, a holographic projection that arises from a vast, underlying network of quantum entanglement. In this view, the universe is akin to a cosmic quantum computer, and the vacuum is its ground state, the most basic program it is running. Every particle, every force, every event in spacetime would then be a kind of computation, a complex pattern of information processing within this network. The vacuum entanglement is the glue that holds the pixels of this cosmic projection together. This transforms our understanding of nothingness completely. The vacuum is no longer just an energy reservoir or a field medium. It is an active informational processor. The forces we have explored, from the Casimir effect to the Higgs mechanism, are not just pushes and pulls. They are the observable outcomes of this deep informational geometry. When two plates suppress certain vacuum fluctuations, they are not just altering an energy density, they are cutting quantum informational threads, changing the local program, and that alteration manifests as a physical force. This perspective offers a potential path to reconcile quantum mechanics with gravity. Gravity may not be a fundamental force in the traditional sense, but rather a thermodynamic or entropic force that emerges from the system's drive to maximize its entanglement, much like the pressure in a gas emerges from the collective motion of molecules. The vacuum, in this grand vision, is the loom upon which the tapestry of reality is woven, its threads spun from pure quantum information. It suggests that the answer to the ancient question of what the world is made of might not be stuff but connections. The silent hum we have been listening to is not just energy, it is the sound of the universe thinking. This long conversation with the void did not begin in a laboratory. For millennia before we had equations or particle accelerators, humanity gazed into the apparent emptiness and tried to understand what it meant. Ancient cultures often saw it not as mere absence, but as a profound philosophical principle. In the traditions of Buddhism, the concept of sunyata, or emptiness, pointed to a fundamental nature of reality where things lack inherent, independent existence. It was not a nihilistic nothing, but an interconnected fullness, a view that resonates, in a strikingly different context, with the quantum idea that particles are transient excitations of an underlying field. Across the world in ancient Greece, philosophers like Democritus argued for the existence of the void, the kenon, as the necessary empty space in which atoms could move. For him, reality was atoms and the void, a duality that would echo for centuries. Yet this idea was fiercely contested. Aristotle famously rejected the possibility of a vacuum, declaring that nature abhorred a vacuum, horror vacui. This was not just a poetic phrase, it was a foundational principle of Aristotelian physics. He believed a void was a logical impossibility, that without a medium to define motion, movement itself became incoherent. This view held immense sway, shaping scientific thought for nearly 2,000 years and reinforcing the idea that emptiness was an unnatural state, something the cosmos actively resisted. The medieval and Renaissance periods saw this debate become practical. When early experimenters tried to create vacuums with pumps, they found pistons mysteriously resisted being pulled, as if an invisible force was holding them in place. We now understand this as atmospheric pressure, but at the time it was often interpreted as nature's literal horror of the void, a physical manifestation of that ancient philosophical fear. This belief was not just about physics, it reflected a worldview where emptiness was seen as a flaw, a corruption of the natural, plenum-filled order of creation. The scientific revolution began to dismantle this fear through cold, hard measurement. Thinkers like Evangelista Torricelli and Blaise Pascal, with their barometers and experiments on mountaintops, demonstrated that air had weight and pressure. The resistance in the pump was not nature's abhorrence, but the simple, measurable push of the atmosphere. The void, it seemed, could exist after all. This paved the way for Isaac Newton's grand vision of absolute space, a fixed, infinite, and truly empty stage upon which the celestial drama unfolded. The void was now permissible, but it was passive, a mere container. The mechanical philosophy of the era saw the universe as a great clockwork, with matter as the gears and the void as the inert space between them. Emptiness was finally accepted, but it was stripped of all activity and potential. It was this sterile, absolute nothing that the quantum revolution would ultimately overthrow. Our modern concept of the quantum vacuum is the latest and most scientifically rigorous chapter in this long story. It represents a profound synthesis of these ancient intuitions. Like the Buddhist sunyata, it sees the void not as a barren absence but as a ground of potential from which all phenomena arise. Like the Greek kenon, it is a necessary arena for activity, though the actors are fields, not atoms. And in a final twist, it even vindicates a kernel of the old horror vacui, but inverts its meaning. Nature does indeed resist a true, classical nothingness, not out of fear, but because such a state is fundamentally impossible according to its own quantum rules. The void is not empty, it is full. It is not passive, it is dynamic. It is not a silent container, but the integral, humming stage upon which the play of physical law performs. This historical arc, from philosophical principle to feared absence to inert container, and finally to active foundation, highlights just how revolutionary our current understanding truly is. We have moved from fearing the void to mapping its forces, and in doing so, we have discovered that the answer to the ancient question of what lies between the stars is not nothing, but the source of everything. The abstract mathematics of the vacuum finds its voice in the classroom, where clever demonstrations turn invisible forces into felt intuition. One of the most powerful analogies for the Casimir effect uses the simple image of two ships adrift on a gently rolling ocean. Imagine these ships anchored parallel to each other, a short distance apart. The open sea around them is filled with waves of all sizes, from tiny ripples to great, rolling swells. But in the narrow channel of water between the ships, only certain waves can exist. Long, powerful ocean swells simply cannot fit into that confined space. Their crests would crash against the hulls. The only waves that can survive between the ships are the shorter ones whose wavelengths match the gap, forming standing waves that slosh back and forth. Outside the ships, the full spectrum of wave energy pushes against their hulls from both sides. Inside the gap, the pushing comes only from that limited set of allowed waves. The greater pressure from the diverse sea outside overwhelms the weaker pressure from the restricted channel inside, and the ships are gently nudged together. This is a direct mechanical picture of how the quantum vacuum works. The ocean is the seething field of vacuum fluctuations. The ships are the metal plates. The restriction on which waves can fit in the gap creates the pressure imbalance that results in a real, physical force. It transforms a baffling quantum concept into a story about boats on the water, something anyone can visualize and grasp. For the more digitally inclined, computer simulations offer another window into the void. While we cannot see virtual particles directly, programmers and physicists can create visual models based on the equations of quantum field theory. One common type of simulation might show a flat, grid-like plane representing a slice of empty space. At first, it appears blank, but then points of light begin to flicker into existence, often in perfectly matched pairs of contrasting colors representing particle and antiparticle. They blossom for a single frame of the animation, connected by a brief, glowing line, and then vanish just as quickly. The screen becomes a dynamic tapestry of these fleeting births and deaths, a silent fireworks display illustrating the constant creative debt of the vacuum. Other simulations might visualize the density of vacuum modes, the allowed frequencies of fluctuation. You might see a three-dimensional landscape where the space outside two boundaries is a rugged, mountainous terrain, representing the infinite spectrum of possible fluctuations. The region between the boundaries, however, is a smooth, flat valley with only a few evenly spaced peaks, showing the severely limited menu of modes that can exist there. The visual difference in complexity and energy between the two regions makes the origin of the pressure imbalance instantly clear. These are not literal photographs of reality. They are mathematical maps, but they serve a crucial purpose. They allow our pattern-seeking brains to latch onto the behavior of these invisible fields, building a visual library for an otherwise purely abstract idea. Engaging with these tools is not just about understanding, it is about inspiration. Encouraging this kind of conceptual play, where we model the cosmos with water waves or animated pixels, is vital. It demystifies the frontier of physics, making it a playground for curiosity rather than a fortress of impenetrable math. When a student sees two toy boats drift together in a ripple tank and hears it connected to the force that might shape the fate of galaxies, a connection is forged. That moment of insight, of seeing the profound in the simple, is what ignites a lifelong passion for discovery. The next generation of physicists will not just learn these theories, they will need to push them further, to ask the questions we have not yet thought to ask. They will be the ones to build the experiments that finally hear the whispers of extra dimensions or untangle the quantum information of spacetime. And they will do it by first turning the abstract mathematics into relatable stories, by playing with the ideas until the universe's deepest secrets feel, for a moment, like an old and familiar tale. The profound nature of the quantum vacuum can be easily misunderstood, its subtle truths often reshaped into popular myths. Let us clarify a few of the most persistent ideas, not to diminish the wonder but to sharpen it. First, the phrase virtual particles popping into and out of existence is a dramatic shorthand that can mislead. It sounds like these particles are tiny marbles materializing from nothing, violating the sacred law of energy conservation. This is not what happens. The uncertainty principle provides a strict accounting rule. The vacuum can borrow energy, but only for a duration so brief it is inversely proportional to the amount. It is a fleeting loan, instantly repaid. The particle-antiparticle pair is not a stable object you could catch. It is a transient disturbance in a field, a quantum ripple that exists only as part of this momentary transaction. They do not come from somewhere else. They are a fleeting excitation of the here and now. This leads directly to a second clarification about the Casimir force. It is tempting to say this proves nothing can do work, but the force does not arise from a true nothing. It emerges because the boundaries, the metal plates, change the configuration of the quantum fields. They edit the guest list of allowable fluctuations. The force is a result of this editing, a difference in pressure between an edited region and an unedited one. We are not harnessing energy from an absolute void. We are manipulating the properties of a field that is everywhere. The work done comes from the energy we invested to create the geometric arrangement that establishes the pressure difference in the first place. A related and alluring misconception is that zero-point energy is a practical, limitless power source waiting to be tapped. As we explored, the vacuum's energy density is uniform, like a perfectly flat lake. To extract work, you need a slope, a difference in energy. The Casimir effect creates a tiny, local slope by using boundaries, but to reset the system and create a cycle, you must always put in at least as much energy as you get out, obeying the unwavering laws of thermodynamics. The vacuum is not a battery, it is the foundation. Its energy is locked into the very structure of space-time, not available for withdrawal without altering that structure itself. Finally, it is more accurate to say the vacuum is full of fluctuating fields, not full of particles. Describing it as teeming with unseen particles suggests a hidden crowd of tiny billiard balls. This paints the wrong picture. The vacuum is better understood as a collection of fundamental fields in their ground state, forever quivering with potential. What we call a virtual particle is just a brief, localized spike in that field's activity. There are no permanent residents, only the field itself, humming with constrained excitement. Clearing away these misconceptions does not make the quantum vacuum any less astonishing. It allows us to appreciate the reality, which is stranger and more elegant than the myth. The void is not a hidden realm of secret matter, but a dynamic stage whose very rules generate the forces that shape our universe. The journey into the void has revealed a landscape of astonishing activity, yet its deepest canyons remain shrouded in mystery. Our map of the quantum vacuum is still being drawn, and the blank spaces on it hold questions that could redefine physics itself. The most glaring of these is the cosmological constant problem. We have a number from cosmology, a gentle push that fits the accelerating expansion of the universe, and we have a number from quantum field theory, a colossal energy density that should tear reality apart. They disagree by a factor of 1 with 120 zeros after it. This is not a small error to be tweaked. It is a screaming siren that our understanding of nothing is fundamentally broken. Resolving this titanic mismatch is perhaps the greatest open challenge in all of theoretical physics. It demands a new principle, a profound symmetry, or a revolutionary theory of quantum gravity that seamlessly weaves the vacuum's energy into the curvature of spacetime. The answer will not just fix a calculation, it will tell us why empty space pushes with exactly the strength it does, and whether that push is truly constant or could change over cosmic time. Alongside this grand puzzle, more tangible ghosts await capture in the laboratory. We have compelling theoretical reasons to believe in the Unruh effect and Hawking radiation, but directly detecting their thermal glow remains a monumental task. Observing Unruh radiation would require sustaining accelerations billions of times stronger than Earth's gravity, a feat far beyond our current engineering. Yet, the relentless progress in laser physics and particle accelerators keeps this dream alive. For Hawking radiation, the hope lies in the ingenious analog systems, where scientists continue to refine their fluid flows and Bose-Einstein condensates, searching for the unmistakable signature of thermal particles born from an artificial event horizon. A confirmed detection in any lab would be a triumph, experimentally linking quantum field theory to thermodynamics and gravity in the most direct way imaginable. Then there is the question of ultimate stability. Is our vacuum, with its specific laws and constants, the true and final ground state of reality? Or are we living in a precarious false vacuum, a local valley that could suddenly tunnel into a deeper chasm? While the probability seems vanishingly small, the sheer existential weight of the possibility forces us to take it seriously. Ongoing precision measurements of particle properties and the fundamental constants are, in part, a check on this cosmic stability, searching for any minuscule drift that might hint at an underlying instability in the void. On the more practical frontier, the dream of controllable Casimir repulsion drives a quiet revolution in materials science. The goal is no longer just to avoid stiction, but to command the vacuum to push. Researchers are meticulously designing metamaterials with nanoscale patterns and exotic electromagnetic responses, trying to write a recipe that flips the quantum pressure from attraction to repulsion. Success here would unlock a world of truly frictionless nanomachines, with components levitating on a cushion of nothingness, and enable sensors of unimaginable sensitivity. Beyond mechanics, the vacuum is being eyed for quantum technologies. The idea of engineering specific vacuum states, or using Casimir cavities to manipulate the spontaneous emission of light from quantum dots, could lead to new types of quantum memories or more stable qubits for quantum computers. Here, the void becomes a tool for controlling information itself. And yes, the human imagination leaps even further to the realm of interstellar dreams. Concepts like the Alcubierre drive, a speculative warp bubble based on solutions to Einstein's equations, rely on a form of exotic energy with negative pressure to contract spacetime ahead of a ship and expand it behind. While purely theoretical and fraught with immense physical hurdles, such ideas often point back to the properties of the quantum vacuum as the only known reference for such exotic energy densities. They are less blueprints and more thought experiments, challenging us to ask if mastering the geometry of nothing could one day mean mastering the geometry of the cosmos. This is the enduring promise of vacuum physics. It is not a closed chapter but an open frontier. Every unanswered question is an invitation, and every speculative dream is a compass pointing toward a deeper layer of reality. The silent hum we have learned to listen to is not just a force to be measured, but a conversation to be continued, a dialogue with the universe that will likely reshape our understanding for centuries to come. Our exploration of the void has transformed emptiness into a universe of action. What began as a simple question about two metal plates has revealed a cosmos where the ground of reality itself is alive with potential. The quantum vacuum is the ultimate foundation, a humming medium of fields whose restless fluctuations are not a side effect, but the central engine. It is this ceaseless quantum jitter that pushes plates together in a silent laboratory, that delicately tunes the inner workings of every atom in your body, and that may very well be the mysterious force stretching the fabric of the universe itself. We have seen that nothing, as we classically imagined it, simply does not exist. Instead, we find a structured plenum where geometry dictates force, where acceleration can conjure heat from cold darkness, and where the mass of every particle is a gift from an omnipresent field. This understanding bridges scales in a way that still feels miraculous, linking the frantic dance of virtual particles at the Planck scale to the stately, accelerating drift of galactic superclusters. The mysteries that remain are not signs of failure, but beacons guiding future discovery. The staggering discrepancy in vacuum energy, the hunt for quantum gravity, the true nature of dark energy, these are the open doors. Each precise measurement of a Casimir force, each observation of a distant supernova, each simulation in a tank of superfluid helium is a step through those doors, bringing us closer to a unified picture of this hidden layer. So the next time you gaze into the apparent blackness between the stars, know you are not looking at an absence. You are witnessing the fundamental arena of existence, a vibrant and energetic medium thrumming with the forces that shape everything from the atom to the cosmos. Its silence is an illusion, masking the profound hum of reality's deepest ground state. If this journey into how empty space generates real forces has reshaped your view of the void, we would love to hear your reflections. Share your thoughts in the comments below and subscribe for more explorations into the profound mysteries of our universe.